let's jump right into this explainer. Today, we're unpacking NumPy, the high-performance engine secretly powering the entire world of machine learning.
So let's dive into this by asking the core question of modern AI. How exactly does Python manage to chew through massive datasets so efficiently? Look, we all know Python is incredibly user-friendly and highly readable, but out of the box, it's not exactly known for blistering computational speed. Yet, it sits right at the absolute center of the modern machine learning revolution. How is that even possible?
Section 1. The Machine Learning Engine, under the hood of AI.
Numerical Python, or NumPy, is really the indispensable lingua franca for data exchange. It's the hidden engine powering almost every computational package out there. Whether you are firing up specialized machine learning libraries or massive data analysis tools, underneath it all, they are almost certainly passing around and computing on NumPy arrays. Section 2. NumPy speed versus Python lists, why loops are holding you back. The core bottleneck here is how data is actually stored and processed. Python lists are wonderfully flexible, right? They're dynamically typed, meaning you can throw an integer, a string, and a float all into the exact same list. But that flexibility comes with a massive cost: slow per-iteration type checks. Every single time a loop runs, Python has to stop and figure out what data type it's looking at. NumPy arrays, on the other hand, are homogeneous. They use contiguous blocks of memory to store a single data type. This structure strips away that overhead entirely, allowing your computer to process the data in one swift, continuous motion. And the benchmark data proves that NumPy isn't just a little bit faster. We aren't talking about marginal gains here. It provides up to a 200 times speed improvement for math functions compared to standard Python lists. And it does this while using 3 to 10 times less memory. It is an absolute game changer when you're dealing with millions of data points. So how does it work? NumPy achieves this incredible speed through a concept called vectorization. Because NumPy arrays are uniform and packed tightly together in memory, NumPy acts as a turbocharger by delegating the loop execution all the way down to the highly optimized precompiled C API level. Instead of Python slowly asking, "What is this?" one by one, vectorization lets the system operate simultaneously over many values at once. To put that into a real-world ML context, imagine computing the L2 distance between RGB images for a computer vision model. Doing this with a standard nested Python loop could take forever, but calculating that exact same distance can be about 2,500 times faster using a vectorized NumPy solution. That is literally the difference between a model taking a few hours to train versus taking several months. Section 3. The magic of broadcasting. Scaling operations seamlessly. Broadcasting acts is the secret sauce of our engine. Intuitively, it's a set of rules for applying binary functions, like addition, subtraction, or multiplication, on arrays of completely different sizes, and doing it smoothly without explicitly writing out slow, nested loops. It automatically matches up the shapes, so the math just works. Imagine you want to center a massive array of data by subtracting a single value from every single cell. Broadcasting duplicates or stretches that scalar value across the array virtually. This duplication doesn't actually take up physical memory in your hardware, providing a highly efficient mental model for smoothly scaling up operations on massive datasets. Section 4. Prepping messy ML data, dealing with NANs and data frames. We all know ML models need incredibly clean fuel to run properly. Missing data can completely break your pipeline. Thankfully, NumPy allows us to detect these gaps, which it calls nans, or not a number, really smoothly using functions like np.inn. From there, you can impute or fill those gaps using statistical measures. But always remember the golden rule of data science here. Always impute after splitting your training and testing data to avoid data leakage. Zooming out to the broader Python ecosystem, NumPy is all about underlying numerical computation and fast math. But for data wrangling, you often want indexing and labeling, which is exactly what Pandas data frames do, built right on top of NumPy. You can smoothly convert a NumPy array into a labeled Pandas data frame using pd.dataframe, clean your data, and then snap it right back to a lightning-fast NumPy array from modeling using the modern toNumPy method. Section 5. The math behind the model's real-world ML applications.
So NumPy directly handles the heavy lifting of artificial intelligence. We're talking about computing those L2 distances in computer vision, speeding up k-means clustering algorithms, initializing neural network weights with random numbers, and solving massive complex equations via its linear algebra module. Make no mistake, NumPy is the software actively crunching the math in the background of your favorite AI models.
The sheer scale of this library's impact is honestly incredible. This open-source tool, initially built by a few rogue graduate students without massive funding, is literally what helps us photograph black holes in deep space. I mean, the M87 Black Hole Imaging Project directly cites NumPy. From the simplest linear regression on your laptop to analyzing gravitational waves, NumPy is there.
Section 6. Powering your ML journey, smooth operations for AI.
By mastering these fundamental array commands, how to create them, slice them, and perform basic mathematics on them, you are giving yourself the keys to build and turbocharge highly optimized machine learning pipelines. It really is the absolute bedrock skill you need before moving on to complex deep learning frameworks.
If you found this explainer helpful in smoothing out your understanding of Python's machine learning capabilities, please hit that like button and subscribe to receive our latest technical content.
Until next time, I'll leave you with this to ponder. As our machine learning models grow exponentially larger, pushing into the billions and trillions of parameters, what future software turbochargers will we need to invent next? What will the next generation of foundational engines look like to keep up with the demands of AI? Keep learning, keep questioning, and I'll see you in the next explainer.